Okay, we will start the class. Oh, is it visible? Screen is visible now? Visible. Okay. So please inform your friends so that they can join the classes. Uh, okay, in the last class, this is very important. So that's the reason just you can inform your friends. Because in the last class we have been discussed about the tensile test. So one of the important experiment it is. In the theoretical things, whatever the theoretical things that relevant to the uh, tensile test that we had a discuss about that tensile strength, what will be the tensile strength, and so how we can define the tensile strength, all the related or the relevant data to the tensile test we have been discussed already. Now today we directly go for the simulation and procedures. uh, Theory parts already over. We have been gone through the much theory regarding the tensile test, and also we have been discussed this stress strain graph, and also you are able to address the what exactly the tensile strength, and also what exactly the deformations, what kind of the deformations we can able to get whenever we are taking the ductile materials, when we are allowing them for tensile operations. So as I told you that yield stress, ultimate stress, and fracture stress are very important, because we need to determine the ultimate strength, fracture strength, and yield strength. Meanwhile, we should understand the elastic deformations and plastic deformations. Okay, definitely in the part of the viva, definitely the examiner may he can ask you about the what you mean by yield load, what you mean by ultimate load, what you mean by fracture load, what you mean by uh, deformation, what kind of the deformations takes place in the ductile material, what about the plastic deformation when we are allowing the brittle material into the tensile test, right? These are the technical parameters or technical things which we need to understand before conducting this experiment. Simply taking the samples and going for the conduction is not a matter. So we have to have this background knowledge regarding the why we need to conduct this tensile strength, what kind of the materials are suitable for these kinds of the tensile test. Suppose once we take the ductile material, what happens, what will be the phenomena. This is what we can able to tell that this is the fracture deformations or ductile fractures takes place. These are number of stages are there whenever we are applying the load on that particular ductile material. That load will be the tensile load. Both the ends are hinged or both the ends are pulled each other. Here you can see this. So this end and this end are under tension, right? Both the ends are under tension. Now we start pulling the material. So what kind of the deformation is takes place? Here you can able to see. This is what we can able to see now. This is we can call it as a stages takes place in the deformations or tensile fracture. How the tensile fracture is takes place. So definitely in the examinations they may can ask you how the ductile material fracture is takes place. See, at the end we can able to get it like this. Cup and cone fractures takes place in the ductile material. In brittle material we cannot get like this fractures. Definitely they can ask you when suppose they can show you the fracture surface, then they can ask you once you look at that fracture surface, you need to determine or you need to answer it. What kind of the fractures takes place in that particular sample? Once you look into that fracture surface, the examiner can ask you. He may take samples and he can show you the fracture surface. Tell me the what kind of the fractures takes place in this material and what kind of the material it is. He may can ask you like this. So once you look at the fracture surface, you need to understand and you need to answer it. Or what kind of the fracture is takes place here. See here, according to the experience, whenever we are using the ductile material for the tensile test, definitely this ductile material will give us to the cup and cone type of the fracture. Right here we can able to see is the cup and cone type of the fracture only takes place in the ductile materials. Brittle material, suppose if you allowing the brittle material into this tensile test, the brittle materials is the flat surface. The once you look into the fracture surface, that fracture surface is look like a flat in the surface. There is no any angle in the flat surface, in the fracture surface. The fracture surface is look like a flat right? So if you could observe that the flattened surface in the fracture surface is look like a flat, hence we can call it, oh, this is a ductile material. This is not a ductile material, sir. This is the brittle material because there is no cup and cone type of the shape. If the cup and cone type of the shape, the fracture, you could identify it, then you can say it is this is the ductile material. This material is undergone to a tensile fracture. So whenever we are applying these ductile materials for the tensile, so they may take these kinds of the shapes. So here we can able to see the image 1 or image A is indicated that both the ends are under tension. Due to the tension, the cross-sectional area will be reduced after the yield. You may yield, it happens at 50 degrees Celsius or 60 degrees Celsius. But that is depending upon the type of the kinds of the material. Some materials will in some materials we can get the yield at around about 40 Newton force. Some materials will possess their yield point at around about 80 Newton force. Some materials for 50 or 60, like that. That will be depending upon the kinds and types of the material. So assume it is that one kind of the material is under suspension of the tensile load. Now we can able to see that the deformation takes place when the yield is occurs in that material. So these kinds of the deformation takes place. As you can see, this is the deformations, which means we can able to see that cross sectional of that sample. Now it's reduced. See here you can see that the cross section will be reduced. Again our load will be the increases. Now number is 40. Now we are increasing the load about 60 degrees, 60 not 60 Newton force. At the range of the 60 Newton force, see again that the deformation is, you can percentage of the deformation is more. See the percentage of deformation is more, which means the cross section area, you can, this is the evidence, the cross section area of the sample will goes on reducing, right? So here there will be the some inclusions or some micro cracks. We can call them as a micro cracks. Some holes or micro cracks will be occurs because of the cross-section area will be reduced. So there will be the percentage of ductility may decreases. So as a result, now we can get the small cracks opens at the middle because of the cross-section area is less. So hence this micro cracks occurs at the certain point of the load. Again our load will be the increases at second stage also. Then our load is keep on continuing and keep on increasing at around about 80 kg force or 80 Newton force. Now all these, because again the cross section area will be reduced, the space will be continue keep on reducing. So all these micro cracks are combined together to form this type of the crack. This is the big crack. So here we can able to see the crack is grows at 90 degree to applied stress. So that's what reason the reason of our load is increases. The micro cracks are combined together to form the big crack. That's what we can call it. So the crack grows as a result of combining the micro cracks or micro holes together. We will get the big crack. So again, if you can increase the load, that tensile, both ends are now continue keep on pulling the ends, both the ends. So these cracks are growth, or this leads to take the fracture. That's this crack grows is increases or propagates, then it reaches to the end. This is the propagation is takes place in the crack grows that leads to take the fracture because this reaches the end, both the ends or one end or both the ends. So hence we can able to see the image D. The here that cracks is reaches to the boundary or line of the material. So as a result, at the end, as you can see the figure E, now we will get the complete separation of the part. So this is, we can say it is a complete separation of the part that is look like a cup and cone type. Right? This is, we can call it as a fracture point, and this is we can call it as a fracture. It's look like cup and cone type. I hope you understand. Definitely in the examination they may can ask you what are the stages are involved in the tensile fractures, how the tensile fracture is takes place, what will be the phenomena or what is the mechanism, how the fracture is takes. Definitely they are asking you. Many times they are asking you how the fracture is takes place. The people are saying is that we are applying the load, so the fracture is takes place. No, what will be the mechanism? That's very important. This is what the mechanism of the ductile fracture takes place in the ductile materials. Now This is you can able to see here. There will be like this. The initially you can see the initial diameter of this sample, how much it is. Now you can observe this both ends. Now you can see the middle, because of that both ends are pulled each other. This will be the reduction torsion area. Later there the fracture is take place in this area. I hope you understand. Now I'm directly taking you into the procedures and simulations so that you can understand better. See, now so we'll take the procedure. So how we need to conduct this experiment. See here, you can able to see this is the UTM machine, right? Okay. So already I think we have been discussed this procedure, right?
Sir, completed.
Yes, completed. No, we only need to take the simulation part, right? Just yes, okay. Just we need to take the simulation part, right? So here we have a simulation, so that now machine is ready for performing the tensile test. Now let's move on to yes. So once they click on that indications, now what happens? Just we can observe. See now, just I'm click on. See, he's measuring the diameter of the sample. Now it's around about outer diameter is 12.62 mm. Now just I click on the button here. Yes. The average initial diameter is around about 12.62. So here the second. So one more trial he is taken. He's also that also gives the same values because it is the same diameter of the throat from this to this side. So the average of the diameter of the sample will be now d is equal to 12.62 mm, right? Yes. Now just I press on the button on this cursor. Now yes. Now we need to take the initial gauge length of the sample. So be careful. So you can just look into this simulation lab so that you can understand better how we need to conduct this experiment. So this virtual lab is very important to know the how we can carry our process in practically. This is an opportunity to know the how to conduct the experiment. See here we are taking the scale and now we are measuring the gauge length of the specimen is around about 194 mm. See, so two punch marks are made at the distance of 2.t. So you need to take the so you can make some punch marks because you need to take the required dimensions, required gauge length. Sometimes gauge length may be vary depending upon the ASM standards. So which ASM standards you need to follow. Based on that, we need to take some different length of the sample. So once you measure it, you can take the punch mark at both the sides. Or else some people are taking some chalk piece and some color codings so that they can mark it. Why we need to mark it? Because thereafter, after conducting the experiment, there will be the changes in their shape and sizes. So that's what we need to take the final length and final diameter of the samples. That's what we need to mark it. So once I push on the button, see here. Right. So these marks is better for thereafter once the deformation, because permanent deformation takes place in the material. We need to find out the final dimension. So what? That's the reason this mark is very important. How he is there the marking. So I hope you understand. Right. See. So all your punch mark will be covered now. So this is the position. This is the way we need to position the samples into the UT machine. So hope you understand now, right? Hope you understand. So once you place the samples in this UT machine, now you can also keep on applying the loads. The load will be gradually increases and increases. That will be already we have been shown you. So there will be the So deformation takes place because these both ends are pulled each other. So here there will be the deformation is takes place, right? So this cross section at the exact middle, the cross section area of the sample will be so reduced, right? So cross section will be reduced. As a result, the length of the sample will be increases. Okay. So wait a minute. So there will be, I think. So once again, we need to simulate this. Okay, yes. So once again, we can observe this. So let's click on this button. Yes. Now this is the measurement of the image length. So this is the punch. Just you can observe the process how it takes place. Okay, fourth step, right. Yes, I think it is complete now. So once we place the workpiece, then the load will be so keep on increasing. Then we will get the so like this deformations. Here we can able to see at this stage now that fifth stage. So the load is increases at this level. Yes, here we can able to see the fracture is takes place. So the cross section area for the exact the middle, there will be the reduction in the cross section area. So here we can able to see the fracture takes place. This is look like once you can zoom it. This is look like cup and cone type of the fracture takes place. So already I have told this. These are the loads you need to calculate or you need to record it. This will be the monitor will be shows these loads and as well the strains that you can. So with the help of these two, now you can you need to draw this stress strain diagram, right? This is very important, and you have to note on all the uh, silent features. We have to highlight all the silent features: lower yield point, upper yield point, elastic limit, proportionality limit, as well as this is the upper yield point, this is fracture point. Already I have been explaining this, but you need to note or you need to mark these all the silent features over the graph in the examinations. This is kind of the brittle material, so cast iron. That also we will see the cast iron how it works. So this is what we can able to see. Uh, up to the fracture is takes place after conducting an experiment. So you need to take the you need to collect the samples, the fracture samples. You need to collect it. Then you can take the final dimensions of the sample. So the total length of the sample, gauge length. That definitely that there will be the changes in the permanent changes takes place in the length that you need to note down, and cross section area of the sample also you need to note down. So up to that, so this is what the way we need to uh, take the gauge length of the sample. See how much there will be the increase or decreases. Definitely the gauge length of the sample will be increases. This is the way we need to get the final length of the final gauge length of the sample. That's very important because we need to calculate the yield strength. So see How we need to calculate the yield strength? Tell me. So here the formula is there. Ultimate load divided by AO means original cross-section area of the sample. Yes, simple. Once you conduct that experiment, now you get all the values. After conducting the experiment, just we can note down the final dimensions of the sample. Thereafter, you have to calculate all these things. It's finish off your experiment. So at the end, as a result, you need to give these all the values. This is the end of the experiment. These are the results you need to make ensure. So your experiment will be wind up. So what are the things we need to calculate at the end? So this is the conclusion or results. The first thing you need to calculate the yield stress. Yield stress is equal to yield load. Yield load, maybe I told you that maybe it is a 40, 60 or 80. That's depending upon the kind and type of the material. So once the material is got yield, then you can note on that. Already I have been explained. So we had a discussion about this in previous class, how we need to take the yield load. Just once the load is dropped down, that is a lower down load is a lower yield point. The previous point, that is upper point, that we can call it as a upper yield point. You need to take only the upper yield point. Then that load, that is the upper yield load, that load divided by the cross-sectional area of the sample. So AO, the cross-sectional area of the sample, already we have been determining the diameter of the sample is around about, I think, 16.25. So you convert the diameter into the cross-sectional wise, then you can take the 40 divided by original cross-sectional area of the sample, so Newton per mm square. So that simplify, you can able to get the Newton per mm square values. Hope you understand that what we can, after simplifying, get some values that will be the yield stress of that given sample. Thereafter, similarly, tensile strength is equal to ultimate load. Here we need to take the ultimate load. So ultimate load, or maybe sometimes it is 80 or 70, the particular material. So 80 divided by again original cross-sectional area of the sample. So simplify it, you will get some values that we can call it as a ultimate tensile strength or tensile strength of the given sample. Modulus of elasticity, which means Young's modulus. How will you find out the Young's modulus? Stress by strain. So you already have a stress values and also strain values. So you need to find out the each and every point of the Young's modulus, right? And the percentage of elongation is very important. Percentage of elongation, that's what the thing we are making the mark, and then we are taking the final dimension with respect to lengthwise and cross-sectional wise. Now you need to take here the formula for percentage of elongation is that. Can you tell me, person, how we need to conduct the, how we need to calculate, or how we need to simplify the percentage of elongation? Percentage of elongation is equal to what? Final length minus initial length divided by initial length into 100. Final length is around about 400. Definitely initial length will be less than that. Initially we are taking the measurements around about 200 mm. So after the conduction experiment, definitely we know the phenomena, the dimensions will be changes, that the deformation takes place in the material. Maybe it is 250 or 300. So now assume it is 300 to 300 minus 200 divided by 200 into 100. So this is what we can call it as a percentage of elongation. Final length minus initial length divided by divided by initial length into 100. That is the formula for the percentage of elongation. And percentage of reduction in area. So final area, because the area will be reduced here, so we need to take the initial area. Initial area is bigger than the final area. Final area is goes on decreasing. So initial area, how much it is? So around about 16.25 diameter is, we convert it. So something where we can get the values. So that is a bigger cross-sectional area values. So initial area minus final area divided by initial area into 100. So once you simplify these values, once we are applying these values in the formula, just to simplify it, then you get the percentage reduction in cross-sectional area. So once you get all these values, the experiment is over. Right? Now, hope you understand. Are you there? Am I clear? Am I clear? Yes. Simple calculations. I have told also the formula and procedure also we have been discussed. So in theory part, whether they report they are mentioning the formula or things. Now we'll check it. So percentage of elongation. Here you can able to see the percentage of elongation is equal to LF means final length minus initial length divided by initial length into 100. This you need to find out at the end, right? So here the cross-sectional area. So percentage of reduction in area is equal to initial area because initial area is bigger than the final area. Final area will be reduced. So initial area, as you can see the formula, right? So initial area minus final area divided by initial area into 100. So that you can get the right. So reduction in area. So here we are writing where is the so Li is the initial length. So Lf is the final length. Here the AI is the initial length, AF is the final length. So this is length, it's not a length, this is the area. So this will be the mistake. This is the initial area and final area. So tensile strength is corresponding to the maximum force. No, that's what tensile strength means corresponding to the maximum load. That is what ultimate. We need to take the ultimate load. Whenever they are asking the what we mean by the tensile strength or how we need to put out the tensile strength. So tensile strength is also we can call it as an ultimate tensile strength sometimes. So whenever they are asking to determine this tensile strength, now you need to take the higher load or ultimate load. So this is equal to ultimate load divided by cross-sectional area of that particular sample in MPa. So megapascal or Newton kilonewton per mm square, or else kg per mm square, anything else, kg per mm square, Newton per mm square, so megapascals per mm square. So whatever it is, the form of load you are applying, that is depending upon that you can take it. So yield strength is equal to yield load divided by original cross-sectional area of the sample. So now modulus of rigidity. So gauge length divided by cross-sectional area of the sample. Slope, that's what stress by strain. This is modulus of velocity means Young's modulus with the help of the slope, because here we are getting the so right now I'm telling that so simulation now. So we are here only you can take this is we are like this the curve we are getting. This is the proportionality limit means so the stress is directly proportional to strain. So whenever the stress values are increases, the same way the strain values also increase. This will happens at some period of time. As a result, we will get the straight line. If it is that stress is not directly proportional to strain, so may we can you can or we can get the curve, say, because these are hard materials, these are the strength materials. So initially, immediately we will not get the much difference between the stress and strain. This obeys the Hooke's law because of the strength materials it is. So it's obey the Hooke's law. Stress is directly proportional to strain. That is up to certain period of time. That up to the elastic limit, we will get the straight line. Now you can apply the slope to the straight line, right? So once you apply the slope to the straight line, now you can take that values. With the help of the slope, by applying the slope, we need to determine the Young's modulus of the given sample. Young's modulus, why we need to find out the Young's modulus? Because we need to know the stiffness of that particular material. Suppose you can able to see this curve. This is the longer curve of the straight line. Some materials will get only this much, half of this. The straight line will be half of this for some kinds of the material. Some kinds of the material, so 2 times of less this, only this much. Sometimes this will be double. This straight line will be double for some kinds of the material, which means only you can say it is a stiffness of that value or stiffness value of that particular sample and material will be high. Larger length of this straight line, you can understand the stiffness value, higher the stiffness value of that given sample. How we need to the stiffness value of the given sample, sir? By applying the Young's modulus with the help of the slope. Young's modulus is a measuring quantity that would measure the stiffness value of the given sample. The stiffness is the first property of the engineering material. How we are depending on how this yield load is important for us. That is what, because of the beginning stage of the plastic stage of the point, that's very important for the engineering purpose. However, stiffness value of that engineering material is also the same, also is a very important for engineering purpose. So that's what the people, they are finding the stiffness value of the engineering material. Thereafter they are finding the yield value of the engineering material. That's enough for the engineers to predict their service life. No need to take sometimes ultimate up to the ultimate. Once they got the stiffness value as well yield value, so that's enough for the engineering applications of that particular engineering material. That technical persons and very experienced engineers are, they can predict their service life, hence they will not conduct the further things, because yield point and stiffness points are very important for the engineering materials, right? So that what stiffness also I can able to define here. Stiffness, meanwhile, the ability of the material to resist the elastic deformations, right? The ability of the material to resist the elastic deformation, that we can call it as a stiffness, because stiffness within that, this property is a processes within the elastic limit. We cannot expect after the plastic, we cannot expect the stiffness value of the engineering material. Stiffness value is within the elastic limit, so this phenomena is to resist the elastic deformations. If that material is allowed to deform elastically, that definitely it will deform elastically, that will reaches the elastic point. Above that we will reach the plastic point. So that is the reason that good quality means the high strength materials will not get immediately deform elastically. They will take much load and time. Hence this load and time we can get the long length straight line. The long length straight line, you can understand stiffness of that particular sample will be high. Hope you understand. Am I clear? Yes. So because why I'm saying all this pin to pin, because this is very important for your external purposes. Definitely that examiner will ask you these questions. That's the purpose. We are not only to conducting is not a matter. So that viva is very important. How you are impressing the examiners, that's very important, right? So that you can get the good marks and more marks, excellent results you can expect. So that's what these are very that's what I am explaining to point, because so you need to answer the from examiner questions, right? So I hope you understand all these things about the tensile stress. Is one of the major experiment, right? Now just I will show us directly simulation of the cast iron. Same experiment it is, tensile test, just we are replacing the mild steel material into the cast iron. So how this simulation is, now we'll see just simulation. Cast iron simulation we need to take because it's extra. So nothing change. Experiment will be the same, but the graph and there is no plastic deformation in the cast iron materials. So you have to have that knowledge also. That's very important. But most of the time we will not take, for understanding purpose we will not take the brittle materials for tensile test. For application purpose, all the kinds we can take. But if you want to understand thoroughly, then better you can take the ductile material graphs, so that you can understand all the silent features, all the silent life of that particular sample. Now tensile test for the cast iron. See here, directly we go for the simulation. Yes. So it's okay, right. Yes, once again we can see this is but mild steel material, not mud steel material. It is cast iron. Everything will be same. Nothing will be difference. So there will be the parameters may dimensions may changes, because however we are changing the materials. Yes. So initial area also calculated here. So initial diameter is 21.28 mm. So area also automatically calculated the simulation lab. So this is a 355.66 mm square. Let's move on to next. Yes, we can just click on to the scale. Now the simulation lab is measuring the specimen length is around about 187 mm. So let's move on to the next. So this is the punching action. So punching it over. Yes. So this is the adjustment that portion. Okay. So up to only we have a simulation. So once you place the workpiece, then that till you can observe the till the fracture you need to observe and note down simultaneously note down the readings. So I think I hope you understand. Now I will take the theory of the cast iron. See here the theory. Everything will be the same. See. Now I will show the stress strain diagram for the cast iron. See here we can able to see the stress strain diagram for the cast iron. So here the fracture is takes place. Once the yield is takes place in that material, so there is no other further features for that material. It's completely fracture is takes place. This is one of the offset method, the proof stress method. Already we have been discussed in the classroom. So why we need to take the proof stress? Proof stress is whenever some materials, most of the brittle materials and most of the polymer materials will not show their yield point directly. Whenever we are conducting the tensile test, because the yield point is very important for us. But some kinds of the material will not show their yield points. But we need to determine that. So that's what there will be one technique, that is the proof stress method, that already we have been discussed in the classroom. I will not take much time to this. So this is we can able to see the fracture surface, how it is brittle material. It's a flat, there is no curve and cone type. This is a completely flat in surface. See, we can able to see the flat surface, we can able to see. These are the brittle materials and cast iron materials, right? There is no ultimate and fracture, there will be fracture point. Here only we can able to see the fracture point.
Hey.
Please kindly mute your mic. Right. See here. See, this is the you can able to see. This is the graph tensile stress strain diagram for the ductile. Sorry, brittle material. Brittle material or cast iron. Cast iron is the best example for the brittle material. Cast iron is a brittle material. Mild steel is a ductile material. This is the one kind of the brittle material cast iron. Now here we can able to see the graph. So see the proportionality limit is also very less. So this is we can able to see, right? Here only we can say it is a, see, this is what yield point. Once we got the yield point, the material will be takes the fracture. There is no yield. There is no yield. There is no like this curve, right? So this is you can say this yield. See the fracture point you can able to see. You cannot expect sometimes the fracture is takes place at the middle, at this end. So wherever it is, where there is a weaker portion, so definitely that portion is, starts from the necking or cracking, that completely fracture is takes place. Brittle metal, see the flat is surface. So you can able to see here. See, the fracture is takes place at this end. So again, you need to calculate all these things for the cast iron also. So why I'm showing you the cast iron also, because of definitely in the examination they can ask you what will be the difference between the cast iron and ductile materials. Means brittle materials and ductile materials. Show me the stress strain diagram for the brittle materials as well ductile materials. So brittle materials are showing like this graphs, and ductile materials already we have been discussed, right? So I hope you understand about this experiments about the tensile test for the ductile materials and brittle materials. Each we are taking to each experiment we are taking the examples mild steel and cast iron. So I hope you understand how to conduct the tensile test, right? Clear it is? Okay. So clear now? Okay. Thank you very much. Now I will wind up this class. Tomorrow again we will discuss the one more experiment. So compression test or else shear test we need to take, right? Shall we wind up now?